and that is the principle in fluids, okay? So in fluids and then gases, that is what we are talking about. So this principle is what we call Bernoulli's principle. Bernoulli's principle. Bernoulli's principle. Okay? So good to go. Right, so the pressure per unit volume. And this, if you take this unit, the pressure here, because the pressure, that's pressure, please, pressure, go, okay, the kinetic energy, how is going, if it is at a certain height, so it has a certain height, it has density, it has a potential energy. This together is a constant for Bernoulli's principle. So this, what this principle means is that let's look at you, a car passing by, and then you standing here. Now when the car passes by, the air in front of you, and then the air behind you. The air in front of you, because the velocity is high, so K is high, okay? If we are at the same level, then let's say potential energy is almost nil, let's look at that. So we have between KE and then the pressure, okay? So if kinetic energy increases, then the pressure must what? Fall, so that the unit volume constant that you have, pressure plus kinetic energy per unit volume plus potential energy per unit volume must be constant, still be constant. Now if this one is, there's no height, then we are dealing with these two. So if the kinetic energy, the car passes, the air in front of you will move fast, the air moves faster. Once it's moving faster, it means its pressure must go down, the pressure goes down. So if this pressure in front of you is low, what will happen to the pressure behind you will be greater. There will be a difference between the pressure behind you and in front of you. Then you will feel like you are being thrown into the road. Okay, that suction kind of thing can be explained by Bernoulli's principle. The same thing applies to our aircraft. Okay, so let's assume this is it. It's a wing. Okay. Now, as the air column passes like that, there's some passing, this is straight. Now, as this one passes, this must go faster so that at the end it meets this. Okay, which means the velocity here is going to go faster, it's going to be higher, and then this velocity will be the same. Now, so far as this velocity of or column of air is going faster, it means its kinetic energy is high. If your kinetic energy is high, your pressure must fall, so the pressure here will be lower. Now here is the same velocity throughout, so the pressure here will go up. So pressure here is greater than the pressure on top, and then the aeroplane will be lifted. Okay, it will be lifted. If the same principle is applied, sometimes it will dive like that, so that you have more like that. So you want it to move this way. So as the pressure flows here more, pressure is low because kinetic energy is high. Pressure is high here, then the plane will move forward. Okay, so these are the principles, the Bernoulli's principle that is being applied in what I've explained here, and then in aircraft. Okay, right. Now let's look at this same thing in some measuring instrument that we have. So we have the Bernoulli principle. So the Bernoulli has something like that. So we are trying to see the pressure here, the pressure there. Okay. Now the principle is the same. Kinetic energy. So here, whatever we have here is constant. And so whatever we have here is also constant. Let's see. It's also constant. Now if the height is the same, then there's no kinetic potential energy, and therefore pressure plus KE is equal to that. Okay, so based on this, we can work out the pressure for this maybe by dividing this and then using the various methods. If it is kinetic energy, if it is velocity we want, the v squared will be in this one, so we can make it the subject and then work for it. So this would be the Venturi. Okay. Now there's another one we call the Pitot one. Let's look at that one too. Pitot static tube. Okay. Now the Pitot static tube goes like that. There's a column inside that's measuring pressure. Okay. So what is happening is that there are holes here. So the hole here is the pressure is going to come out. Okay, that is going to be the static pressure. Okay, and then this is moving with the velocity. Now, if it is the same height, then what do you call it? PE is out. So that the total pressure will be equal to static pressure plus your kinetic energy per unit volume. Okay, right. So this is the principle. So this is the principle for this one. So depending on what you want, if you want density, pressure is given by what rho times what your gravity times height. That is it. Okay, and then you have it. So depending on what you want, this is an expression like that. Okay. So depending on this is the total pressure. So depending on what you want, you work it out for. Okay. So there is the Pitot static device. Okay, right. So that is that for the Bernoulli's principle. Let's move on. Now let's look at the column of air moving. This, let's say, air is moving like that. Now this column of air, we can actually estimate the pressure. So if this column of air is moving, pressure is equal to what? Force of the area. Okay? This is the same as mass times gravity over area. Okay? So this is a cross-sectional area. This is the length. So you can do substitutions. Okay? So the pressure with which it is going. Okay? The mass. This is we can in terms of A and L. So volume is equal to cross-sectional area times height. This cross-section times this will give you the volume. Okay, area cross-sectional area times the length. Okay, so in terms of A, you can have pressure is equal to what your mg, and then you have your A as what B over L. It comes out as what mg/L v. So that's the volume. This is an expression. Okay. So these are the ways, some of the methods you can use, depending on what values that you have. So this is the column of air. So if you want to say you want to find the work done is equal to force times distance. Okay, and force is equal to what? Pressure times what? Area. So the area, pressure times what is going to be pressure times area times the distance. The distance that is moving. Okay, let's say that column is L. So we put in the values and see. So the work done is this. Okay, put in the values and see. So this, your pressure, the column, the formula. Okay, the rho times what? Rho times what? Gravity times height times your cross-sectional area times your cross-sectional area times what? Your length. But remember, cross-sectional area times length is more or less giving you what? Volume. So these are the kind of manipulations you can do with the question. Okay, so depending on the question, you can find out. If you do not want to use this as volume, you know, area is equal to this area is equal to what? Pi r squared. And this L, okay, is the length there. Okay, and so one over is, of course, this length that you're talking about is also L. Is this length that you're talking about. So equations can be manipulated just by substitution level. Just that you follow the principle, and then you can work out to derive so many formulas. Okay, that's. Alright, so that is that. Now let's look at another one. If this is moving with the magnetic energy K. Okay, this moves with kinetic energy K. Alright, then the KE is equal to half mv squared, which is the same as, you can represent this one by mass is the same as density times what volume v squared. Then you can say half rho. Volume can also be said as area times length v squared. Okay, now this is the kinetic energy. Now let's say we want power. The power is equal to what? Energy over time. So this is the energy, kinetic energy. It is moving, so it is moving with the kinetic energy. So this is the same as say half rho A L v squared over T. L over T is also V. So that's going to get what? Rho A times what? Velocity. That's another thing here. Then we're going to have half rho A V to the power 3. This is the power. Okay, this can also be expressed as half rho area cross sectional area. So what? Pi r squared V to the power 3. Okay? Right, so this can also be used. So depending on whichever way you want to look at it, you can go like that and then you get your answer. Right. Yeah, so remember this half we have here is because we have the average, it's average of the velocity v, whereas what u. But if it's the same, if the velocity component is 1v, then you don't need to find the average. So in that case, this equation will become what? Power is equal to what? Rho, because it's 1v, so it will just is the same one of the things. You are not going to find the average of the thing. So we're going to rho pi r squared v to the power 3 as the power for this moving column of air. Right. So this is one way to go about it. Okay. But if you have different velocities, okay, then you must, or let's say you started with 0 to v, then this is how it's going to be. But where you have a different velocity, that will be adjusted for. But where it is v constant from the scratch to the end, the same v, then you don't need to find average. It's just v times, and then that comes out like that. So if you start with the initial velocity v, moves with the same velocity as constant velocity, this is what we are having. Right. Okay, so that is that. Move on. The wave that we have, the tidal waves, and then we have the waves itself falling, and then so if we have this on the sea, and then we have this water. Okay, moves. Okay, it's moving like that. Okay, this upwards and downwards movement is the wave itself. It has energy. Now the levels, maybe at one point it's here. Another level, the sea level rises here, and this is due to the moon, attraction between the moon and the earth. Okay, so if the moon comes closer, then the attraction is greater, and then you can have more the change in the level. Okay, so this change is what we are referring to as the tidal. Okay, the tidal function. Okay, the tidal wave. So that's the tidal. So that in itself is also another form of energy. So tidal energy. So this tidal energy will depend on the attraction between the earth and the moon. Okay, and then we have a way of calculating attraction between two bodies is Q. The force is proportional to Q1, Q2. Okay, right, and then it's also inversely proportional to the distance between them. We'll get there. When you get there, we'll discuss it so that F becomes equal to K, Q1, Q2 over R. And this has an expression depending on what is happening. If there's two bodies, having bodies, of course, gravity comes in and so on. So we'll get there. And this, we also take into account the 4 pi factor and so on. Right. So up to this point, we'll leave it here. When we get to forces, we'll discuss that. So move on. Now let's move on to the elasticity. Let's say this is an elastic material. Now I can stretch it. It will still stretch and then come back. Okay, it's still elastic there. It's still within the elastic range. Okay, and this Hooke's law will work. Okay, so that the tension is proportional to the force you apply. Now at the point when you get to the limit, when you go beyond that, if you stretch it, it will not come back. If you stretch it, it will not come back. So this will be the elastic limit. If you stretch it, it will not come back, but it will expand. And that point is where we say it is plastic. Plasticity here. And to get to a point where the plasticity is also exhausted. So this is the plastic limit. Okay. And then beyond that point, you have the breaking point. Okay. Okay. Now you can extend this principle to look at metals, other materials and so on. Now stress is giving us the force per what area, and then strain is giving us the extension per length. Extension per length. Okay, if you have stress over strain, we call it the Young modulus. Okay, so it's more or less you have this over that. So it's going to flip up. We're going to have FL over AE. Okay, this measures the constant we call the Young modulus. Okay, now if two bodies have their particles well packed like that, then they are able to vibrate too. Okay, they can easily hit other and then come back. Such a body, if they are closely packed, they will conduct sound energy very well because they are elastic. The Young modulus is high. Okay, so if the stress is high, okay, so it means if you apply pressure over a small area, the vibration goes in, and then they are able to hit other, and then the sound is transferred. This will give you the reason why sound will move faster in solids than in liquids and then in air. Okay, in that order. If you are closer, you can vibrate and hit each other and translate the energy. Okay, right, or transfer the energy. Right. So that is one principle. So these formulas you can calculate them.
Now about the second question.